In the
Okay.
calendar, though, there are no other sessions at this time.
Okay. No problem. Let it be. Just wait for a second. Okay. So, what is the first concept in week 8? I think it's moment generating function, right?
Yes, sir.
So, mainly, I think you can see there are two main concepts. One is moment generating function,
MGF and CLT, yes.
CLT. So, these two are main concepts of this week, and these two, I mean, you will get some. Uh, Obviously, you will get some questions related to these topics. Okay, so first we'll see the concepts. Okay, and along with if you have any doubt regarding activity or something, so we'll see that also. Okay, is my screen visible to all of you, everyone?
Yes, sir.
Yes, sir.
Okay, this is general book. Okay, so let's start with moment generating. This is about your week 8. Okay, so first is what is the moment generating function? So by the name, I think it seems to clear to all of you why it's called moment generating function. Why it's called moment generating function? Because this generate the moments for your random variable. Okay.
Distribution.
So generate moments means, so like see, if I'm saying expected value of x raised for I, so basically this sometimes called the ith moment. Okay, this is nothing but ith moment. Okay, so similarly, okay, we'll see. So suppose I have random variable x. Okay, so mgf of in short it's called mgf. So mgf of random variable x is denoted as nothing but mx lambda. This is equal to expected value of e raised power lambda x. Okay, so I think in the lecture video, it has been defined for zero mean random variable, right?
Yes, sir.
Okay, so don't worry. MGF is true for any kind of random variable. Okay, so basically, general definition of moment generative function is this: mx lambda. Lambda is constant. Is nothing but expected value of e raised power lambda x. So suppose this is the definition in general. So basically, uh, suppose your x is discrete. Okay, then how I will get expected value of e raised power lambda x? So it will
It's
be
sum overall
summation of e raised power lambda x into
into P of X.
p of I mean PMF of that random variable, right?
Huh.
Correct. And if x is continuous,
Integral of the same thing.
so I
Fx
can
of
get
X.
expected value of e raised power
P.
lambda x integration of e raised power lambda x into PDF of that
Yes.
random variable. Okay. So I mean it should be exist. This expectation should be exist in general. You know, expectation should be exist, right?
Yes,
So
yes.
this formula is okay so far, everyone. So
Yes, sir.
basically, why it's called moment generating function. So you know what is the expansion of e raised power x? It's a one
L
plus x
um,
plus x
plus
square by two
x square
factorial
by 2
plus
factorial, x cube plus 3 factorial, and so
and
on.
so on, right? Now, if you see, I have expected value of e raised power lambda x, right?
Yes.
So I can write down this expected value of if I will expand this e raised power lambda x instead of x, I have lambda into x. So it will be 1 plus lambda x plus lambda square x
X
square
square
divided by
by
2
2
factorial
factorial.
plus lambda cube x cube divided by 3 factorial plus so on. Correct. So if I will take the expectation inside the bracket, what I will get? I will get 1 plus
1 plus lambda, sorry,
this
lambda
things, right?
expectation.
So
हाँ हाँ
expected value of lambda square x square divided by 2 factorial, correct? Plus expected value of lambda cube x cube divided by 3 factorial, right or not? Correct?
yes sir.
So it will be 1 plus lambda times of expected value of x plus lambda
Mm,
square
this one
divided
by
by
3
2 factorial
factorial.
expected value of x square plus lambda cube divided by 3 factorial, it will be expected value of x cube, so on. So basically this generates the moment. What is the moment? So this will this is called the first moment.
हाँ
Okay, expected value of x square is called the second moment.
second moment.
Similarly, like the third moment and all. So this is something called your, I can define the moment generating function of a random variable actually. So
So
in the yeah, please go ahead.
the moment here you are referring to as different instances while we are expanding the exponential uh, mm,
Uh-huh.
this when we are expanding this e to the power x,
Uh-huh.
the instance of each expectation is known as the moment, like
Yeah,
respective moment.
basically expected value of x raised power I is called the ith moment. Okay, so if I will see expected value of x, so this will call the first moment. Expected value of x square, this will call the second moment. Expected value of x cube will be treated as the third moment. So this all moments will get now when you will study about next not next week 10. So there is one called method of moment for parameter estimation. Okay, so there these kind of things are very useful. So for now you can just treat it expected value of x raised power I, we are treating this as ith moment. Okay, so since this expected value of e raised power lambda x, from this I can get this first moment. So this is expected value of x square is the second moment, and like this. Get it? So similarly, you can see first moment is what? So in general, I can say ith moment will be nothing but coefficient of uh, lambda raised power I divided by I factorial. Got it? Hello?
Yes sir.
Okay.
Yes, sir.
Okay. Yeah. So next is in the lecture video, I think sir has defined this MGF for zero mean random value, right?
Yes sir.
So there is, there is not that much different in the this concept. So things are the same. Only difference is this random variable. Mean of expected value of this random variable is zero. Okay. So this MGF is basically defined in general. You can define for any kind of random variable. It's there is not any uh, necessary and sufficient condition. That random variable should be zero mean. It's not required. Okay, so basically suppose, okay, let's take one example. Suppose I'm saying x is following normal 0 comma sigma square. Okay, so what is the mgf of this? You can derive it, but you can keep these things by heart. It's a basically it will be very useful. Mx lambda is nothing but e raised power
Lambda
lambda
Sigma
square,
square
square
sigma
sigma
square
lambda
by
square
square
2.
by
by
2.
2.
Okay, so I think sir has told
Yes
suppose
sir.
you are sleeping in the night and someone came to you and asked what is the mgf of normal 0 comma sigma square, you should immediately reply that for that. Okay,
Five
so
star left and right.
sorry.
Sir, mention five star
Okay,
in the
even
lecture.
though even though I'm mentioning or not, it's okay, let's say 5 star, 7 star, whatever. Okay, so basically, key idea is this key idea of this moment generating function. Why it's called moment generating function? Because it generates the moments for that random variable actually, and you can define this moment generating function any kind of for any kind of random variable. Okay, it doesn't necessary to it should be defined for the zero mean random variable. Okay, if it's asking in the question you have to find out for zero mean random variable, then I'm hoping you guys are aware about how you can get the zero mean random variable, right? How I can get the zero mean random variable?
X minus mu.
Yeah, I mean I have to just do the x minus expected value of that random variable. Okay. So far it is clear to all of you.
Yes, sir.
Okay. So let's see any example of activity. Let me take. Okay, so that you can get the idea how we are doing this. Just a minute. It's okay. So for this question, let's say x is uniform 1, 2, 3. We have to find the moment generating function of centralized x. So first thing is we have to I mean we have to do we have to find what is the meaning of centralized x. Okay. So for that, what we can do?
So we can calculate for the mean,
Yes,
for x, e of x, and then we can calculate for x minus mu, and then we can calculate the MGF for that centralized thing.
centralized.
Means
So it's
mean
x.
zero.
Yeah, x is uniform 1, 2, 3, right? It's a discrete uniform. It is asking you to find the MGF of centralized x. Okay. So as we know what is the meaning of centralized means we have to do x minus expected value of x. Correct. So
Yes, sir.
let's define this as another random variable y. So that means I have to find the MGF of random variable y. That means I have to find the my lambda. Okay. So far so good.
Yes, sir.
Now, what is the expected value of x?
2.
So expected value of x will be 1 into 1 by 3 plus 2 into 1 by 3 plus 3 into 1 by 3. So it's the 3, 2, 5, 6 divided by 3 is the 2. So, okay, now what is the centralized version of x? So now what is your y? Y is nothing but x minus expected value of x. So it will be 1 minus
Minus
2.
1
That means
half.
minus 1,
0
2
and
minus 2, 0, 3 minus 2, 1. And what is the probability for each y?
1 by
It
3.
would be same, sir. 1 by 3.
Yeah, it will be same. Now, so I have to find out this MGF of this case, these things, right? And I know what is the MGF. MGF is nothing but expected value of e raised to lambda y, correct? And for since it's a discrete, so I know how I can define the expected value of x. It's nothing but summation of x into px. So instead of x, I have e raised to lambda y. So it will be summation of e raised to lambda y into probability y equal to y or not. Now, so we have to take the value of y. So what is the value of y first? Minus 1. So it will be e raised to minus lambda. And what is the probability when, okay, so write down y equal to minus 1 plus e raised power 0 into lambda, probability y equal to 0 plus e raised power 1 into lambda, probability y equal to 1. So it will be e raised power minus lambda into 1 by 3 plus it will be
It's just
something
1
power
by 3.
0, 1 by 3 plus e raised power lambda into 1 by 3. So it's nothing but uh, e raised power minus lambda plus 1 plus e raised power lambda divided by 3. Is there any option? Last option is the correct.
Yes, sir.
Let's see. Yeah, so last option is the correct. So is everyone getting the idea for this?
Yes, sir.
Yes, sir.
Okay. So any do you any doubt regarding this activity 8.1?
So sixth question.
Direct answer. What is the value of sixth moment? So first of all, you have to understand the meaning of what is the sixth moment actually. What do you understand by the sixth moment? And okay, before
Coefficient
going,
of e raised to x of
okay,
6.
To the
yeah,
power 6.
before going to that, suppose MGF is given to you, correct? So can you find out the distribution of that random variable?
Yes, sir.
Yes, sir, we can.
We can, right? Suppose forget about these things. Suppose I'm saying you have given, suppose I'm saying I have one random variable y. Okay, I have a random variable y and mgf of this random variable y is given to me as 1 by 3 plus 1 by 3 into e raised power minus lambda plus 1 by 3 into e raised power lambda. Okay, suppose this scenario is given to you and I have gave you some three or four options and I asked what is the correct option, I mean what is the correct pmf of pdf, I mean or pdf of that random variable. Okay, let's say what is the correct pmf of that random variable. So from this can I get the pmf?
Yes, sir.
Yes, sir.
Okay, and be careful while you are going to checking the option, sum of the probability, first of all if it's pmf sum of the probability should be 1. Okay, I mean this 1 by 3 1 by 3 1 by 3 is 1. So from here can I get as you can see it's what 1 by 3 into e raised power, this is something 0 into lambda, right? Plus 1
Yes,
by
sir.
3 e raised power minus 1 into lambda plus 1 by 3 into e raised power something 1 into lambda. So as you can see from the definition itself, so what is the e raised power lambda x actually? So it's nothing but e raised power let's say it's a summation of e raised power lambda x into p of x equal to x, right? So suppose x is taking some value, let's say x1 x2 x3. So that means what? So it will be e raised power lambda x1 into probability at x equal to x1, right? Plus e raised power lambda x2 probability x equal to x2 plus e raised power lambda x3 into probability x equal to x3, right? That is something. So what I'm trying to say here, so this what is the probability and this is the same, correct? So this will be value, and for this value what is the probability? Similarly a value of your random variable, and for this random variable what is the probability that random variable is taking that value. Similarly this is the value of the your random variable and what is the probability that this random variable is taking that value. So similarly I can say my random variable is okay, so for this example it will be correct option will be like this. For this random variable for this example random variable taking value 0 with the probability 1 by 3. It is taking value minus 1 with the probability 1 by 3. It is taking value 1 with the probability 1 by 3. It is clear to all of you?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. Okay, so any doubt in the concept of this MGF?
No, sir.
No? Okay. I think someone asked the question of sixth moment, right? So can you tell me what was the your approach for that? Hello.
Incredible, sir.
Yeah. So I was asking what was your approach for this? Okay. So since it's a sixth, first of all, it is asking about we have to find out the sixth moment of normal 0 comma 3, right? So what is the meaning of normal 0 comma 3? Suppose I'm saying my random variable x is following normal 0 comma 3, correct? So that means mean is the 0 and sigma is
Variance
5,
is
Variance
3.
is 3.
variance is the 3, correct? Now what is the mgf of normal distribution mx lambda?
E power lambda
E
square
raised to
sigma
lambda square
by 2.
sigma square by 2.
Okay, but be careful in this case expected value of x is 0, right?
Otherwise, you
Yes,
have
sir.
the factor of mu
Yeah,
into
correct,
lambda
correct, correct,
also.
correct, correct, correct. So okay, and how okay, what is the meaning of sixth moment? So it's the expected value of e raised to power no
6.
not e raised to power expected
Expected
value of
value of x to the power 6.
x raised to power 6, right?
Huh.
Now, so this will call the sixth moment, right? Of my this normal 0 comma 3. Okay, so how you should, okay, so this means it's a coefficient of lambda raised to power 6 divided by 6 factorial, right?
Yeah.
Yes, sir.
Okay,
Yes, sir.
now what is okay, so first what we can do for this case, any idea?
So I know, like it wasn't mentioned in this course, but I know that to find the rth moment using MGF,
Uh-huh.
you have to take the rth derivative and equate lambda to 0. But
Okay.
in this case, that's very tedious because you have to differentiate it 6 times.
Yeah, yeah, yeah. So what should we do? Any idea?
I actually did that way, RS derivative way, because I couldn't think of anything.
God.
So everyone has done that like that, right? I think someone else. What is this Jamboard, Anupur? No, it is doing that. Okay, let it be. Let's come to point. So that thing is also correct. What is the problem with that? I mean, we can do that one, right?
Also, you can.
Uh,
It'll just be long, that's all. But like that's how you can do it.
Sorry.
It'll just be a little long, that's all.
Okay.
Tedious.
Okay.
It's tedious,
No.
Kind of
yeah.
tedious.
Okay. That's okay. No worries. So this is okay. This is okay. I mean, coefficient of lambda raised power x, lambda raised power 6 divided by 6 factorial will be sixth moment of that, right?
Yes, sir.
Okay. Now, so as we know, mx lambda is this one, right? Mx lambda is e raised to power lambda square sigma square by 2. So from here I can say e raised to power 3 lambda square by 2, correct?
Yes, sir.
Yes, sir.
Sigma square is the
Yes, sir.
3, right?
Yeah.
So what is the
Yes,
e
sir.
raised to power x expansion of e raised to power x? 1 plus x square by 2 factorial like that, right?
Yeah.
So if I will expand this one, what I will get? 1 plus 3 lambda square by 2,
Yeah.
correct?
Plus
Yes.
Plus 3 lambda square by
lambda.
2 whole
The whole
square
square.
divided by 2 factorial,
2 factorial. Yeah.
plus uh, 3
Plus 3
lambda
lambda
square by
square
2
by 2. The
whole
whole
cube
cube by
divided by
3
3
factorial.
factorial, correct?
Yes.
Plus so on. So thing is that you can observe here. So I can do 1 upon 2 factorial into why am I stopping here? Because we'll see. Because if you do the square of this, I will get 9 lambda raised
Because
power
we are
4
getting that coefficient of
divided by
lambda
4,
power
correct?
6.
This we will get, correct?
Mm.
Plus 1 by 3 factorial into 27 times lambda raised power 6 divided by 8. So we have to find out the coefficient of lambda raised power 6 divided by 6 factorial. So I have lambda raised power 6. Okay. So to get the 6 factorial, what I can do, I can multiply it and divide by 6 factorial.
Yes.
Okay. So from here, coefficient of lambda raised power 6 divided by 6 factorial will be what? 27 times 6 factorial into divide by 8. 3 factorial into 8. Okay. So I mean, yeah, we have to calculate it. We'll get the answer. I think is this correct answer? Let's calculate 27 into 6 into 5 into 4 into 3 factorial I can do. So that 3 factorial will get cancelled out and 8. So it will be 3, it will be 4, 4 will get cancelled out. Is this correct answer? 15 times 27.
Yes, sir, it's correct.
Yeah, it's 405. Yeah.
So now you got the idea how we can proceed, right?
Yes,
So
sir.
basically, expected value of x raised power I can get with the, it's nothing but coefficient of lambda raised power I divided by I factorial. Okay. So as while we are doing this lambda square raised power cube, so from where I can get the idea, it is going to be lambda raised power 6. So I to get the lambda raised power 6 divided by 6 factorial, I can multiply it and divide by 6. Okay, clear this?
Yes, sir.
Got
Yes,
it?
sir.
Okay. Yeah. So any other doubt related to MGF? So now I think you can find out the MGF, correct? And suppose MGF is given to you, and then you can find the distribution of your random variable. Okay,
Yes, sir.
Yes,
clear?
sir.
Now, so what's next? And okay, can I find out the MGF of sum of random variable?
So if they're independent, it's the product of their
It's a
MGFs.
product up there, right?
Yeah.
That's we can do directly also. Okay, let's do one. Okay, just let me know if I'm any topic is missing out. Right? Suddenly I recall. Suppose x1 and x2 are following IID x. Okay, for example, and this x, let's say, is nothing but Bernoulli p. Okay, now I have defined one random variable y as nothing but sum of these two random variable. Okay, so okay, before going to that Bernoulli p, let's say it's IID x. So what is the MGF of y? Okay, so MGF of y means what? So I can see, as you can see, expected value of e raised power lambda y, right? So what is the
Yes,
y?
sir.
Y is nothing but
X1
expected
plus
value of e raised
x1
power
plus
lambda
x2.
x1 plus x2. So now
Mm.
expected value of e raised power, I can write down e raised power lambda x1,
Into e raised to lambda
e
x2.
raised power lambda x2. Since x1 and x2 are IID, means they are independent. So I know when variables are independent, so then expected value of x into y is what? Expected
Expected
value of
value of
x
x
into
into
expected value
expected
of
value of
y.
y.
Correct? So similarly, these two are different things. So it will be expected value of e raised power lambda x1 into expected value of e raised power lambda x2. Correct? Now, so this
Yeah.
is the true. This is the true when suppose x1 and x2 are independent only.
Independent.
Now, suppose here I have mentioned, but it's these x1 and x2 are IID. If these two are IID, that means expected value of e raised power lambda x1, it will be same. Both will be same, right? Both will be
Yes, sir.
same as the x for
Mm.
the original. So that means
So
expected
it's
value of
whole
e raised power
square.
lambda x whole square. Okay, this is something we can do directly. Okay, this is okay for everyone. Clear? Yes, no.
Yes, sir.
Yes, sir.
Yes, sir.
Now let's take one more example that will give you a clear idea for that. Uh, so as I told you, let's say x1, x2 are IID x, okay, and y is nothing but I defined x1 plus x2. Now, what and this x is suppose this is IID, this is Bernoulli P, IID Bernoulli P. Now, before going to that, what will be the mx lambda? Okay, so what is the x? It's nothing but it will take value 1,
0 and 1.
0, and
0.
with probability p and
1 minus p.
1 minus 1.
right now. So what will be the mx lambda? Expected value of e raised power lambda x. So that means e raised power 0 into lambda 1 minus p plus e raised power 1 into lambda into p. Yes or no?
Yes, sir.
Yes, sir.
So from here it will be 1 minus p plus p into e raised power lambda. Correct? This is the
Yes, sir.
MGF of your x. So why I find out this one? You'll get within a minute. You will get. So what is the my lambda? It will be m x1 plus x2 of lambda, and it will be expected value of e raised power lambda x1 plus x2. Since I said these are independent, so these two are independent, so it will be expected value of e raised power lambda x1 into expected value of e raised power lambda x2. So that means I can say mx1 lambda into mx2 lambda, right? See, this is the mgf of random variable x1 and this is mgf of random variable x2, correct?
Yes, sir.
Yes, sir.
So can I say, okay, so there is one general statement if xi's are independent, then mgf of sum of random variable is equal to product of their individual mgf, right? So let it be. So what? Okay, since these x1 and x2 are IID, so I will say mgf of both random variable will be same, right? So that means it will be square of these things, right?
Yes, sir.
Yes.
So what we can do, simply I can find out the my lambda by doing the square of the this mx lambda. So it will be 1 minus p plus e raised power lambda times p. So I mean once you will square, you will get the mgf of your random variable. Okay, so it will be 1 minus p square plus e raised power 2 lambda p square plus 2 times p 1 minus p e raised power lambda. So this will be this is nothing but mgf of my random variable y. Okay, this is clear to everyone.
Yes, sir.
Yes, sir.
Yes,
Sorry,
sir.
Yeah, 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 please.
can you just show the 1 minus p thing which you expanded over here? Like, yeah,
This one.
that's yeah. Give me a second. Okay, done. Done.
Done? Okay,
I
okay,
missed that part. Okay.
okay, no worries. It's clear so far. All the things are clear to everyone
Yes.
now.
Yes, sir.
So let's come to call the one of the very important concept in statistics, that's called the central limit theorem. Okay, in short we are calling it as CLT. So which is the full form of short form of the central limit theorem actually. So how CLT is defined actually? Okay, that's the idea. So basically CLT is nothing but, so normally we are so as you once we had started the week 7. So what was our assumption? Not assumption. What was the you can say important thing? Important thing was we have to consider the IID's case, right? So what central limit theorem says in general? So suppose I have an IID random variables x1, x2, xn. I'm following this is I'm saying it is following some distribution x, but with IID, right? Then sum of these random variables. Okay. Basically, before going to central limit theorem, are you aware about the law of large number?
Yes, sir.
What is that?
Yes, sir.
About the sample mean that, like the confidence interval of the sample mean, like
The bound.
x bar, yeah, the bound of like x bar minus mu being greater than delta.
Okay. So basically, large law of large number says it's nothing but law of large number says when when we will increase the sample size, okay, then mean will get closer to the average of the whole population. Okay, what is the meaning of mean will get closer to the average of whole population? Suppose I'm doing the same experiment for a large number of times. Okay, suppose I'm doing any experiment for a large number of times again and again and again and again, then the average of the outputs of those experiment will be close to the expected value of that random variable. Did you get it?
Sir. How much we are close is what we find in that
Close and all, I mean accuracy and all we are.
probability of.
Yeah, that's why there are that theorems and all is there. So basically law of large number, what is the idea of, I mean what is the meaning of law of large numbers? Suppose, okay, suppose you are rolling a die, correct? So what is the expected value of rolling a die? I think it's a 3.5,
3.5.
right? So now if I will perform this experiment for a large number times, again and again and again and again, then average of the outputs of those experiment, right?
Huh, that will be
Average of the
3.5.
outputs of those random variable will be close to this expected value. Okay, that is the meaning of law of large number basically. Okay, so that idea is useful in case of central limit theorem actually. Okay, did you get the meaning of this law of large number, everybody?
Yes, sir.
Okay,
Sir.
so what is the central limit theorem says basically? So central limit theorem says nothing but let me add fresh page for this. Start from here. So central limit, nothing but suppose I'm saying I have an IID random variables. Okay. Suppose I'm saying let x1, x2, so on, xn are these all are IID random variable x. Okay. So I will come to the definition which sir has discussed in the lecture video. Before that, I would like to start with basic idea of central limit theorem actually. Okay. So this suppose this and I think sir has taken the mean zero, right?
Yes, sir.
If
Yes,
I'm not
sir.
wrong. So let's take in general. I will come to that point. Okay. So suppose that each exercise, okay, each having mean mu and variance, let's say
Sigma square.
sigma square for each random variable, right? Then what central limit theorem says that distribution of your x bar will be what? It will be close to mu. Or simply you can say distribution of your x1 plus x2 plus xn. Before going to that, let's come to that summation of distribution of summation of xi will be close to standard normal distribution. Okay, do you know what is the standard normal distribution, right?
Mu
Mu
0,
zero, variance
variance 1.
1.
Yeah,
Variance 1.
1.
0, 1.
So basically it's nothing but, so it says x1 plus x2 plus so on, let's say xn. Okay, let's do for this. So what is the meaning of this? So okay, what will be the mean of this x1 plus x2 plus xn?
The sample mean of that.
No,
Oh,
not,
no, no.
it's I'm
Ah,
asking
then
this
you
summation of
divide by
xi.
n.
Okay, what I'm saying, if x1 x2 xn are IID x, so what will be expected value of this?
Mu, sir. Mu.
No,
N
That's
into
N
mu.
into mu.
N
n into
into
mu,
mu.
right? I'm not,
Yeah.
it's not mean, I'm not going to mean first. Okay, I'm asking about this n mu, right?
N
And
mu.
what will be
Yes,
the
sir.
variance of this xi?
N square sigma
N
square.
into sigma
N
square.
into
Oh wait,
sigma
n
square,
into
right?
sigma
N
square.
sigma square.
Right?
Yeah, yeah.
So basically what this is, so distribution of this x, so summation of xi, this distribution of summation of xi will be standard normal, will tend to standard normal. So this means this minus n mu and divide by sigma square root of n. Okay, are you getting this more? Yes, no?
Uh, can you repeat
Sir,
No,
this one?
sir. Can
what?
you please once again?
Okay, so what central limit theorem says, if I have x1, x2, xn are I have suppose IID random variables, okay,
Okay.
then n will be large, okay, then the distributions of sum of your random variables will be close to the
Will tend to
approximately
normal or
normal
0, 1.
distribution. Okay, so you can find out for sum of random variable, or you can find out for mean of that random variable, because if you are going to find the mean of that random variable, that means in a way I'm going to do the sum of that random variable. Okay, basically.
But
So
how
it's
did you get this, sir? X1 plus x2 and so on up to xn
hmm.
minus n mu is e of x1 plus x2 plus so on xn
Yeah,
by
and
Variance
Okay.
of
What is the
x
standardization?
minus mu by sigma.
Suppose
Okay.
I'm saying
Huh.
x is following normal mu comma sigma square, then how will I will get the standard normal x
X minus
minus
mu
X
mu
by
minus
divided
sigma.
by
mu by
sigma.
Yeah,
sigma.
yeah.
So in
Okay,
the
okay,
place
fine.
of x, I have sum of these random variables, right?
Okay.
And mean of this is n mu, and standard deviation of this is. So idea is this distribution of this will be close to the approximately, I mean it will be approximately normal, standard normal distribution. That means when n is going to be large. Now come to that the definition explained by sir. So sir has taken the x1 x2 x10 is following IID x with expected value of x is 0, right? Yes or no? And
So zero
variance
mean.
variance of x is sir has taken as sigma square, correct? So what sir has done? So distribution of y is what? X1 plus so on xn divide by under root n, correct? So what sir is take? It will be close to the normal 0 comma sigma square. So whether it's true or not for this from this. If I'm not going to take sigma here, okay, then distribution of this will be normal 0 comma sigma square or not?
Yes.
Yes, sir.
Are you getting? Okay, everyone is getting the point. How much similarity is there between these two?
Yes,
Yes,
sir.
no?
Yes, sir.
Yes.
Yes,
Because
sir. Yes, sir.
mu is 0, right? So this will become 0, correct?
Correct.
If I will take sigma as 1, not sigma as 1, if here is 1, that means I have divided by sigma, correct? If I'm not going to divide by sigma, I will get the sigma square. That's all.
Yes, sir.
Okay.
Here
So,
the sir,
huh?
one second, sir. Here the variance you've taken is sigma square, right?
Ha ha.
So the denominator, how is it root 10?
Denominator
Here
y.
y in y,
Mm-hmm.
as per the above thing, whatever you have written, if you
Mm-hmm.
that is a general case,
Mm-hmm.
and in this case, x1 plus x2 plus so on up to xn minus nu will become 0 by
Okay, okay. No,
instead of
no,
sigma root 10, right? How is it only
no,
root
no, no, no.
10?
We are not we are not doing here standardization.
Uh, no, no,
We
no.
have a
I'm
not.
saying here you have taken
Okay,
variance
okay,
of
okay.
x as sigma
One
square.
second, one second. I'm saying distribution of this y will be this normal 0 comma sigma square, right?
Correct.
This is meaning. So what is the expected value of y? It will be expected value of x1 up to xn divided by root n, right? And mean of all random variable is 0.
Yeah.
It will be 0 by root n. Now what will the variance of y? So that means variance of x1 plus so on xn divided by root n,
Mm, yes.
correct? So that means what? I will get 1 by n
1 by n.
variance of
The
this,
variance. Yeah.
correct?
X1.
So I will get
Yes.
n sigma square divided by n. So
N.
it's a
Yeah.
n sigma square, right? So
Sigma
variance
square.
of y
Okay.
sigma square. It's the same as variance of y sigma square.
Okay.
Okay.
Okay, sir.
So these two
Yeah.
are the basically same. So only difference is
Okay. Okay.
we have done here standard normal. It's a here I'm treating normal with mean 0. That's all.
With, okay.
Clear? Okay. So this idea is
Okay.
clear behind the central limit theorem.
Yes,
Is there anyone who has doubt? So basically, central limit theorem is, for central limit theorem, whatever distribution is following your random variable x, whether it's a discrete, whether it's a binomial, Poisson, exponential, continuous, uniform, whatever, doesn't matter. For a large number of sample, when n is going to, I mean, when n will tend to infinity, distribution of your x1 plus x2 plus xn will tend to your normal distribution. Okay, is this okay to everyone?
yes, sir.
So whenever you have question related
Sir,
to
where this root n is coming from?
sorry,
Root n, if you'll go down, like if you'll go down, yeah,
uh,
this root n x1, it will be only n, or
no, no, it's not about average.
No, you have defined y as x1 plus x2 and so on up to xn by root n, is it?
Root n, yeah.
Okay, fine.
Okay. So suppose I'm taking, okay. So what central limit theorem says, suppose whatever I'm defining y, right? For when n is going to be when n will tend to infinity, distribution of this y will be approximately normal. Okay, so here I have defined, suppose I have defined y as summation of xi. Okay, then I can go with the standard normal also, and I can go with the normal 0 comma sigma square also, doesn't matter. But key idea is it will follow the normal distribution. Okay, I mean, did you get
But
the?
when will it follow normal 0, 1, and when will it follow 0
Doesn't
sigma
matter. No,
square?
no worries, no worries about that. So these are
Okay.
just a two different form. Okay. In the lecture
Okay.
video, sir has taken this. If you want, then you can go by this. So while you
This.
are going to solving the questions, right? So it's more preferable to convert your random variable in standard normal format, because uh, we have to take the values from the standard normal table, that
Table.
exact value. Okay.
Okay.
So it's a good to go with this. So okay, it's the same as, see, if I am taking here y as x1 plus so on xn divided by root 10, I'm saying it is following normal 0 comma sigma square. So it's the same as if I will say x1 plus x10, this is divided by sigma root 10 is going to be normal 0 comma 1. It's the same.
Yes.
Okay, so it's doesn't matter. Okay, so idea is clear behind the central limit theorem, everybody?
Yes, sir.
Anyone
Yes, sir.
anyone have any doubt?
So I have a doubt, like when do you say sample size is large enough? Like
Yeah, sir. Actually, in statistics, we are going to consider when n is more than 30. So they are considering as a large samples. Okay. So, but it should be more than large, as you can take. If I mean large means suppose n is 1,000. So it will be more close to that. I mean normal distribution. You will get your curve bell shaped curve, properly bell shaped curve. Okay, so it's not there is any exact value for this, and it will be follow uh, for this exact value of an, it will be bell shaped curve. But its idea, key idea is and should be large means normally we are considering large samples when sample size is more than 30 actually. Okay, because if you see five samples, so it's possible like you are getting the something like that, something possible. So when you will increase your sample size, so you will get your curve, I mean some your curve like bell shaped curve actually. So I mean, so your mean will be here, mean will be here, which is 0 kind of things. Okay, so this is something about bell shaped curve and all. Okay, is it okay for everyone so far?
Sorry, sir, if I'm asking it again.
Mm-hmm.
Uh, if you'll go to the notes which you are writing,
Uh,
there is one root n over here. So, like, if I'm missing something from the back classes or something like that,
mm.
like, is it like where this root n is coming from? Am I missing something from the previous
No, no,
class?
no, no. Okay, so this is something. Suppose I'm saying I have. Okay, so one key thing for the central limit theorem, whatever you have given, right? Sum of your random variable or mean of something like that. So convert that random variable into standard normal. Okay. So how I can convert this standard normal? Suppose I have x follow normal mu comma sigma square. So x minus mu comma sigma will be divided by sigma will be standard normal variable, right?
Yes, yes,
Yeah,
yes,
this
yes.
is the one thing. Now come to the point. Suppose I'm saying x1, x2, xn are IID random variable x. Okay. Each random variable have mean mu and each random variable have variance sigma square. Then before going to that, suppose what is the expected value of sum of random variables? It will be n times mu.
Yes, yes,
And what will
yes.
the variance of sum of your n random variable? N times sigma square, correct?
Because there are n number of
N number of random and all are IID, so I can add.
okay.
Okay. Now so what is the distribution? Suppose I have defined y as sum of your random variables. Okay, let it be. Let's do a refresh. Okay, so suppose I'm saying x1, x2, xn. These all are IID x. Each xi have mean because it's IID, so mean and variance will be same. Okay. Now, so I'm saying what central limit theorem says basically. Suppose I have defined y as a sum of random variables. Okay. So what
Yes.
central limit theorem says, y minus expected value of y divided by standard deviation of y will be normal, standard normal distribution when n is going to be large. So this is the central limit theorem basically. Okay. So whatever your x size is there, whatever your original distribution of x is, whether it's Bernoulli, I will come to that square root of n. Let me complete this. So whatever it's a Bernoulli, Poisson, whatever, if n is large, and I have defined y as the random variable as x1 plus x2 plus xn, then y minus expected value of y divided by standard deviation of y will be approximately normal distribution. Okay. So since I'm doing y minus expected value divided by standard deviation of y, so it will be standard normal distribution. So this key idea of central limit theorem is clear to all of you?
Yes. Yes.
Yeah.
So,
Yes, sir.
Yes, sir.
if we did, instead of, if we didn't standardize it, like if we didn't subtract expectation of y, would it be normal? Like if you didn't do minus expectation of y by standard deviation of y, would it be normal n mu and sigma square?
No, no. Can you repeat? Y minus?
So if you just did y by root n,
Mm-hmm.
then would that tend to normal n mu
Yeah,
and
0
sigma
comma
square?
sigma. That's the both thing we have done, right? Okay.
No, so if you didn't subtract the expectation,
Okay. If you are not subtracting, that means its mean is 0, right?
huh?
Yeah. Okay. I will take these two. Okay. Let me do. Okay. So now, what is the if y is summation of xi? Then what is the expected value? What will be expected value of y? It will be n times of mu.
N times mu, yeah.
And what will be the variance of y? N times
It will
of
be n
sigma
times
square, right?
sigma square.
So
Yes.
standard deviation of y will be what?
Root n sigma.
Root and sigma. So that means I can say y minus n mu divided by root and sigma is nothing but normal, standard
Huh.
normal, right?
Yes.
Now, in the lecture which what sir has taken, okay, so okay, this is okay, root and this okay, I think who has
Yes,
asked
sir.
this root and
Yes. Yes. I have asked. I have
yeah,
asked.
now
Yeah.
it's clear from where root
Yeah.
and came.
Since we are removing the root, like
Uh-huh.
root and yeah. Yeah.
We are doing the standard deviation of y.
Yeah. Yeah.
So you are saying y is nothing but x1 plus xn divided by root n, correct?
Huh.
Okay. So what is the expected value of y? But it should be clearly mentioned what is the expectation of x size. Okay. I think sir has took expected value of x is 0, if I'm not wrong, right? So do you want to take me very expected value of x 0 or in general?
In general, sir.
Okay, in general, then it will be n times mu divided by root n,
Divided by
correct?
root n.
So it will be root n mu, right?
Yes.
So and what will the variance of y? So it will be 1 upon n times of sigma square, right?
Hmm.
So it's very simply sigma square,
Sigma
right?
square.
So it will be y minus under root n mu divided by sigma will be your standard normal distribution. That's all.
Okay, so that's, but if you didn't do, if you just took y by sigma,
Uh-huh.
would that be normal root n times mu
Ah,
and
that's the normal transformation, right?
ha, yeah, yeah, yeah.
That's the same
So
thing.
it's the same thing. It works the same way.
It
Okay.
always works. Okay. Okay. So far, it is clear to all of you. Key idea of central limit theorem and another things. Yes.
Yes, sir.
No.
Yes, sir.
It's clear to all of you.
Yes,
Yes.
sir.
Okay.
Yes, sir.
So should we move to the any question related to that?
Yes, sir.
Yeah. Let's do one more question.
Example.
Hmm.
Okay,
I
the
think
question.
we can take this first example also, right? So key idea is about central limit theorem. Just convert that into the uh, standard normal, okay? Because at the end, when n is going to be large, it will be then. So average life of a coffee machine, okay? So is 5 years and with a standard deviation of 1 year. Assuming that the lives of these machines follows approximately normal distribution, find the probability that mean life of a random sample of 16 such machines fall between 4.6 and 5.4 years. Okay, but that is the it has been asked about this question is mean life of your random sample. Okay, so first of all, uh, what is the mu? 5 and variance is 1, right? I mean sigma is the 1 and sigma square will be 1, correct?
Yes,
Yes,
sir.
sir.
Assuming the lives of these machines follows approximately a normal distribution. So that means let's define x as a random variable which is nothing but life of machine, correct? What is this? Normal distribution. So that means it's following 5 comma 1, correct?
Yes, sir.
Sir.
Find the probability that mean life of random sample of 16 such machines falls between 4.6 and 5.4 years. So let's say mean life of machine. Okay. So mean life of machine is what? Let's define as y. And what is this y? Y is nothing but x1 plus x2 plus so on x16, right? 16 machine, right?
Yes,
So we have to find out for this. So it says we have to find the probability that mean life of machine will be lies between 4.6 and 5.4. So these things all about my question, correct? But I know to use the central limit theorem and all, so I have to convert in standard normal format, right? So if y is x1 x2 x I mean x1 plus x2 plus up to x16 divided 16, so what will be the distribution of this? What will be the mean of this distribution?
16 into 5.
16 and
16 into 5, sir.
why 16? 16 to 5.
And
So
mu.
n mu, sir.
So it's a n mu divided by 16, right? Because y is the mean
Ha.
life, right?
Then it'll be
Ah, so
5.
mu
So it's
only
It'll be
5.
5.
mu.
Okay,
5.
suppose x1, x2, xn are IID x, then if what is the x bar distribution of x bar? It's nothing but mu comma sigma square by n, right?
Yes, sir.
Yes, sir.
So it will be 5 comma 1 by 16, correct?
Yes, sir.
So far so good.
Yes, sir.
So now we have to find out this. So what I have to do? I can convert in standard normal, right?
Ha.
So what I have to do? I have to subtract the mean and divide by the
Divide by standard deviation.
deviation, right? So I have to do 4.6 minus 5
Minus
divide
5.
by square root of 1 by 16
Ah, 1 by 4.
less than y minus 5 divided by square root of 1 by 16 less than 5.4 minus 5 of divided by 1 by root 6. I think 1 by root 16 means 1 by 4. So 1 by 4 is
1 by
0.25.
4.
0.25, right? So it will be probability minus 0.4 divided by 0.25. And what about this? This is nothing but let's treat as z. Okay,
Ha.
because it converting it as standard normal. So it will be 0.4 divided by 0.25. So far it is okay for everyone.
Yes, sir.
Yes, sir.
Yes, sir.
So minus 0.4 divided by 0.25 will be minus 0 point not 0 point, so minus 1.6. Okay, less than g less than 1.6. So as you know from the continuous word, if a is less than x less than b, then I can say f of b minus
F
f
of
of a,
b minus f of a.
correct? So these things I can write down as fg 1.6 minus fg
Minus
minus 1.6,
1.6.
right?
Ha.
And since it's a standard normal, so I suppose this is the standard bell shaped curve, right? So this is symmetric. Suppose this is mu. So due to symmetricity, suppose this is a, this is minus a. So probability less than z less than minus a is same as probability z greater than a or not.
Yes, sir.
Yes,
So
sir.
this is same as, right? So what is the meaning of this one? First of all, fg 1.6. So fg it's probability g is less or equal to 1.6, right? Because it's a CDF. And probability G less or equal to minus 1.6. So since it's a standard normal variate, so what I can do? So probability Z less or equal to minus 1.6, it will be same as Z greater or equal to 1.6 or not?
Yes, sir.
Yes,
Sir,
sir.
1 minus we have to do.
No, I will
No, no,
do,
no.
but
Z greater
this
than equal to 1.6.
this is just correct, right?
Ha. Yeah, yeah, yeah.
Okay.
Just
Yeah, just this
interpretation. Yeah.
this is same as this one. Now, since I have to find out the means from the CDF value, so I can convert. I can do these things as 1 minus probability G less or equal to 1.6, right?
Yes,
So
sir.
it will be probability G less or equal to 1.6 minus 1 plus
Plus
probability
probability.
G less or equal to
Ah,
1.6. So here is 2 times probability G less or equal to 1.6 minus 1. So 2 times probability G less or equal to 1.6 minus 1. So that means 2 times it's nothing but FG 1.6, right? Minus 1. So I
Yes,
think
sir.
this value will be given to you, will be provided to you. So FG 1.6. So this is right 0.9452. So 2 times 0.9452 minus 1. I mean, you will get the answer. So key idea is you have to convert in standard normal variate. Suppose sometimes, okay, suppose you are getting FG0, right? So there
that's
is no need to
0.5.
give the value of this like things. What is the value of this FG0?
Half.
0.5.
0.5. So because
Half.
FZ0 means what? Probability Z is less or equal to 0, right? So in the case of standard probability Z are less or equal to 0 means this region is point half and this will be point half. Okay. So far so good, everyone.
Yes, sir.
Yes, sir.
I think is there any other question or I think you are able to do it?
So can you just do one more question from me?
Which one?
Just any one of the questions.
Okay, have you attempted this one anytime or
I went over them, sir, but I did not understand how to solve them.
which
I'll
one?
try them again now.
Okay, which should we do? Third or fourth?
So third one.
Okay, third one will be good for everyone.
Yes, sir. Anyone is
Yes.
fine.
Also,
So,
actually fourth
Anyone you
because
do.
it's going from Poson to normal.
Okay, let's do fourth one. In a way, it doesn't it will not
No,
be
doesn't
better.
make a difference.
Yeah, because central limit theorem says it will be standard normal.
Hmm.
Okay. So okay, so let's do the fourth one. So number of accidents in a certain city is modeled by a Poisson random variable. It says with an average rate of 9 accidents per day. Okay. So what has given? So it has been given mu is 9, right?
Yes, sir.
Okay.
Sigma square is also 9.
And sigma square is also right because in case of Poisson, mean and variance are same. Suppose that number of accidents on different days are independent. Okay, use the central limit theorem to find the probability that there will be more than 3300 accidents in a certain year. Suppose that there are 365 days in a year. Now, so it says okay, so what is the y can I define the total number of
Sum of
accident in a year,
huh.
correct? Okay, so mean is 9, the sigma square will also be 9, that means sigma is the 3. Now, so as what is this mean? This is 9 accidents per day. Okay,
Yes, sir.
right? So what about expected value of y?
365 into 9.
365 into
365
9.
into
365,
9.
365
3285.
into 9, right?
Huh.
But
3285.
we have to consider for whole year, right? So what is the value of this 365 into 9? Anybody?
3285.
3 2.
85.
Okay. Now, and what is the variance? Variance will be same, correct?
Yes, sir. Same 365 into 9.
Variance will be same.
I
No,
think
no.
so. No?
Variance will not be same because so y is, let's say I'm defining xi is the number of accident on ith day. Okay. So what is
Uh-huh.
your y? Y is nothing but summation of I is equal to 365 xi, right? So it's the
Yes, sir.
variance of summation I is 1 to up to 365 xi. So it will be 365 times variance of xi, right?
Yes, sir.
I think it's the same.
Same only.
Yeah, it's
It's
the
same,
365
same.
into
sir.
9.
Yeah, it's the same. Yeah, sorry. Yeah. Because mean and variance are same in case of poison. Yeah, sorry.
Exactly, sir.
Actually, yeah. So variance is also same, right? Now, so we have to find out the probability this number of accident in a year is greater than how much? 3300.
3300.
3300. Correct. So now what I have to do from here? I can convert into standard normal, right? So that means
Same thing.
probability y minus what is expected value of I? 32
3285.
divide by square root of y, that means uh, it will be 3 into square root of, I mean square root
365.
of
365.
365.
3285 simply, right?
Uh-huh.
Greater than 3300 minus 3285 square root of 3285,
Yes, sir.
correct? So that is probability. What is this? This is simply, it will be g.
Z.
Z.
Z greater than 15 divided by
2
this.
plus
What is the
this.
square root of this 3285?
57.31.
57.31. And what is the value of this 15 divided by 57 point? I mean,
So 0.267.
0.2617, right? Okay. But this value is not given, right? So we have, what I can do, 1 minus probability g
You
less or
said less
equal to
than 0.27. Huh.
2617. So 1 minus fg 0.2617. So whatever your value is there, if the value is given to you, 0.2617.
So it's a
Yeah,
0.603.
0.603. Okay. So 1 minus 0.603. So it's nothing but 0.397. So if that's correct or not. So 0.397 will be inside the bracket. Yeah. So is this clear? I mean, did you get the
Yes,
idea?
sir. Got it, got it.
So key thing is what we have to convert into the standard normal
Huh.
variable. Okay.
So, sir, nothing. You just have to find mean variance and then
That's all.
standardize it. That's
That's
it.
all. That's all. That's
Okay.
all.
Okay.
Because central limit theorem says for your n, whenever your n is large, the distribution of some of your random variables will be close to the normal distribution. Okay. So far, any doubt?
No, sir.
Anybody?
No, sir.
Okay. I think week 7 and week 8 is easy, right? There is
It's
not
fine.
that much difficulty there. Okay, so just give me a minute. I will have some water. I will come back to you. Okay.
Okay, sir.
Yeah. Hello. Yeah.
So you're
So
audible.
yeah. Okay. Okay. Thanks for the confirmation. So yeah. So what's the next? I think there are some just a intro of some distributions, right?
Yes, sir.
Yes, sir.
Okay.
Gamma,
That's
alpha,
yeah.
Ram.
Cauchy.
Gamma, alpha, Cauchy, beta, and all, right. So those are just a intro of some distribution of your continuous world. So okay, so let me just go through that. What is the PDF and all? Okay, so that's not. I mean, that is useful for the next week onwards actually. But if you talk about this quiz and all week 8, so I think till now it's okay. Okay, I mean this central limit theorem and MGF is sufficient.
But
But
as far as the quiz 2 point of view, MGF and central limit theorem are enough, is it?
yeah, enough.
Okay, thanks.
Okay, but let's go to that, because suppose some question is coming out to be there, then uh,
Okay,
don't complain. Yeah, there is not
okay.
So
topic
you
to.
did share the weightage of the week 7 and week 8 as 20%, if I'm not wrong.
No, no.
20.
It's I think, approximately 40% of from 7 and 8, 40% of 5 and 6, and 20% from week 1 and 1 to 4.
Okay.
Not exact, approximate. Okay. So let's say about some linear combination. I think you guys are familiar about the linear combinations also, right? But let's discuss. Okay, because there are topics. So linear combinations of, I think it has been discussed about normal distributions, right?
Yes, sir.
Okay. But it's also true in case of general also. General you can do. You suppose x1, x2, up to xn are independent normal distribution. Okay. Suppose I'm saying I have this information. So it's not about IID. I mean, means are not same. Suppose this xi, simply xi is following normal with mean mu I and sigma I, variance sigma I square. Okay. So I have suppose one random variable which is defined as a1 x1 plus a2 times x2 plus so on an times of xn. Okay, which are nothing but linear combinations of your. So what will be the, okay, what will be the distribution of y? Okay, so what is the expected value of y? It will be a1 mu1 plus a2
E2 mu 2.
and so on. Just a
Huh.
simple calculation, right? And what will be the variance of y?
Uh,
A1 square
A1
sigma 1
square
square, right?
sigma 1 square.
A1
A2.
square sigma 1 square.
A2 square, sigma 2 square plus so on something, an square, sigma n square. So this is true in case of any distribution, right? It doesn't matter about even though it should be normal. But the only thing is you should be aware about what is the mean and what is the variance of that distribution. Okay.
Yes, sir.
So now there are some distributions. First one is called gamma. Let's see what is the basically gamma distribution. Okay, so what is, okay, before any one of you can tell me what is the gamma, if you are aware about this.
Gamma is a function to
Okay, gamma
calculate
is gamma
covariance,
function. We
right?
have this done, I think, in mathematics, right?
Ha ha.
Gamma
Yes,
function is
like
okay.
large integral with exponents.
Correct,
Hmm.
correct. With exponent e raised power minus beta x. I mean that parameter can be different
Something
actually.
like that.
Hmm.
It depends on. I mean, you can take different parameters also. That doesn't matter actually. So I mean, it's a, see, basically gamma distribution we can use in in the field of business engineering a lot. There are, I mean, there are a lot of uses that about gamma distribution actually. Okay, so you will see the use of gamma distribution in case of Bayesian estimation, which we will study in week 10 also. So basically what is the gamma distribution? Okay, so what if you see binomial distribution Poisson, so these all are distribution of one parameter, right? Normal
Yes.
distribution is the distribution of two parameter,
Hmm.
correct? So exponential distribution is the distribution of one parameter, right? So but gamma distribution also is the distribution of two parameter. I mean, it contains the actually two parameter. One is called the shape parameter and one is called the, another is called the scale parameter actually. Okay, so I think you guys will be like, so what we are discussing here. Okay, let's discuss. Okay, so what is the, okay, suppose I have random variable x is, I'm saying it is following gamma distribution with parameter alpha and beta. Okay, where alpha is nothing but shape parameter and beta is the scale parameter. Okay, so scale parameter is nothing but is, I can treat as the rate parameter, right?
Yes, sir.
What is the rate by which rate this there is change in my distribution, you can say. So
Based on
basically,
Can
the
you
frequency.
put more light on the gamma distribution? Reason being that I haven't studied math one.
okay, so gamma distribution is nothing but is first. first is it's a it has been come from the gamma function actually. Okay, so those both are same. Okay, I will come to that point. Okay, let me take this PDF. So PDF is approximately x raised to power alpha minus 1 into e raised to power minus beta x actually. Okay, so this is the something, and in the denominator I think I mean if you solve not solve if you see, so I can you can write down this beta raised to power alpha x raised to power alpha minus 1 e raised to power minus beta x divided by gamma alpha. Okay, this is treated as gamma alpha actually. So what is the this gamma alpha? So gamma alpha I can write down the alpha minus 1 factorial, right? I think
Yes,
if
yeah,
I'm
n
correct.
minus 1 factorial,
Yeah,
correct.
we can find the value of gamma. So this notation is called gamma. If I'm putting any value, let's say gamma 3, so gamma 3 is same as the 2 minus 1 factorial. That is the something. So this is the PDF of your my gamma distribution in this case. Okay.
Sir,
Yes.
PDF these two lines, is it? You have done fx.
Yeah,
What is the
these two are
symbol?
the same. Okay, so if I'm
What is the
putting the,
symbol?
yeah, if I'm putting
That
the this proportional sign, that means
proportional sign.
yeah, I'm not taking this constant quantity.
Equality. Yes, yes.
Yeah,
Okay,
I'm
fine.
not taking this constant quantity. If
Okay,
I'm
okay.
putting equal sign, so I'm taking this PDF actually. Okay, so basic, I mean this is something, I mean one kind of distribution which is called the gamma distribution actually. What, okay, so someone was asking gamma function, I think, right?
Yes, sir.
So gamma function is nothing but, okay, correct me if I'm not wrong, if I'm not making. So gamma function is, suppose I have any this it's the nothing but one extended form of factorial thing actually, factorial function, right? So suppose I have told you this gamma of let's say I'm going to take this gamma of y. Okay, so how I can find this gamma of y? Anybody?
So there's an integral form also, right?
Yeah, integral form of actually.
Like integral 0 to infinity t to the power y e power minus t or something like that.
Actually, we have two parameters a
Huh.
and p. Okay,
Mm.
so gamma function is okay. Suppose, okay, one second. Okay, before this notation is treated as gamma. Okay, so suppose I'm saying gamma 3. Let's start from this basic idea. Gamma 3 means it's a 2 factorial. Okay, and suppose, I mean simple, in if you see in case in general, so gamma n is same as n minus 1 factorial. Okay, so this notation is nothing but it's something Greek letter. I mean that, let's not go that there. So basically, gamma function is your nothing. It's defined as complex numbers actually. Okay, okay. I think it's. Are you getting my points, or it's going to difficult to for you?
No, so please tell.
Okay.
It's fine
So
only.
it's actually, I mean, we need the gamma function to prove the
Proof
normal
there. Okay. So
difference
basically,
mean and
gamma function.
sigma.
Suppose I'm taking y. Okay. So this general definition says, so it's we can integrate from 0 to infinity because this y is greater than 0. So I think it's for any variable we can find out, right? I mean, it's suppose I have t, right,
Huh.
and minus t dt, right, in
Minus t
general.
dt,
Okay,
yeah.
this is
Yes, sir.
something called the gamma function. I think I'm correct, right here.
Yes, sir, that's correct.
Yes, sir. Yes, sir. Yes, sir.
Yeah. So this is something gamma function is defined. I mean, it's something called the gamma function. So from here, we are going to study about gamma distribution. Okay, so as you can see, this for this gamma distribution there are two parameters. One is called the shape parameter and another is called the scale parameter. Okay.
Yes, sir.
Yes, sir. So far clear.
Okay, okay. Yeah. So now, I think so far it is okay for everyone, or any query?
A bit confusing.
Uh-huh. Where this gamma function, huh?
Yeah, and everything is bouncing from gamma function.
Okay, okay, no, no, don't get that confusion at all. So basically, any gamma function, we can define it this like that. Okay, I mean, I can, okay, basically for gamma function, it should be. I mean, what is the range? Basically, range should be 0 to up to infinity. It will be positive random variable actually, not random variable. Range will be positive actually. So it's a, I mean, this definition you have to uh, assume, not assume, you have to somehow keep in your mind. This is something called gamma function. Okay, if you talk about the graph, then I can plot the graph about the gamma distribution also. Okay, so I mean, this is something called the, I think, okay, let me do it. One thing. Let me do it. Suppose this things, and this thing. Okay. Now, so what about x raised power alpha minus 1? What graph will look like? X raised power alpha minus 1. It will be something like that for in general. Yes, no. When x is greater than 0. Am I audible, right?
Yes, sir.
Yes,
Uh-huh.
sir, you're audible.
Okay, so okay, so this will be x power alpha minus 1 or not? Something like that. For x greater than 0. See,
Yes, sir. Yes, sir. It
suppose I'm
it it
I'm
would
saying x
depend.
cube, x cube.
Hmm.
Okay, then x cube is like this, right? But for
Yes,
x
sir.
greater than 0, it will be only this part,
Yes, sir.
Yes.
correct? So for
Yes,
x
sir.
raised power alpha minus 1, I will get something like that.
Yes, sir.
And what about exponential part? E raised power minus beta x. So it will be like this, something.
Yes, sir.
Yes.
Okay.
But shouldn't the alpha be greater than 1?
Alpha is greater than.
For that shape, shouldn't alpha be greater than 1?
Alpha is, we are taking alpha is greater than 0 actually. Alpha and beta both should be greater than 0, strictly greater than 0. Okay. So this is basically shape parameter. I mean, this is called the shape parameter. This is called the scale parameter.
So, but in case if the alpha takes value 1,
Mm-hmm.
would the graph stay true?
Yeah, it will be. I mean, so if alpha is 1, so you will get something e raised power minus beta x only, right?
Right, right.
Yeah.
Okay,
So that will be okay. So accordingly, I mean, we are plotting this graph in general actually.
okay.
Okay. So this will be x raised power alpha minus 1 and e raised power minus beta x. Alpha should be greater than 0 and beta should be greater than 0. Okay. So what will be the product of these two?
So something like there'll be one peak and then it'll fall.
It will be peak and it will be fall. Why?
Like intuitively, that should happen.
Yeah. So something like that. You will get e raised power minus beta x and x raised power alpha minus 1. You will get. So this is I mean something. If you can see this is shape and scale. I mean that's why it decide about shape of your that distribution, right? And it gives a scale. Scale means I can say simply rate parameter. Rate parameter means if you can define rate. Oh, okay, what is the rate? Rate means 1 by beta
Huh.
actually. And a gamma distribution is nothing but also, since we know about normal distribution, mu comma sigma
Yes,
square,
sir.
right? So if I will do is, suppose I'm saying x is following normal mu comma sigma square, right? Not mu, let's say 0 comma sigma square. Then square of this variable will follow gamma distribution. We can cross verify also. Okay, I think as per the response, I think you are getting difficulty, right? What's
It's
the
a
things
lot
are
of
going.
information at once.
Yeah, it's a lot of information. Okay, so okay, before, okay, let's not go that level. This gamma PDF is okay. I mean, you and for more exploration, just go through what is the gamma function actually. Okay, so you can actually gamma function is defined as like this. From where we are going to study about gamma distribution. Okay, so for now, what you can do, you can just keep in your mind this PDF of your gamma distribution actually.
So for
So
the scope of this course, is it enough that we remember the PDF and
ah, see, for more, if you want to study more and more and all, so what,
detail about gamma function? Then
then you can do.
okay,
I mean, you can do, or else we can discuss also. There is not
okay,
any
sir.
problem. But thing is that you people are not aware about this gamma function, right? So I think that's why you are facing difficulty. What's the things we are I'm writing here, right?
Actually, we have not learnt about this function in any of the previous courses, so we are
I
learning it
think
right.
in
Yeah,
mathematics they have taught, right?
Sir, the
It was
gamma
in
function
separation.
wasn't there
it was
because
not
No,
we
there.
don't
maths
have the
two,
double
maths two,
integral
it was not there.
first.
Hmm.
I think
Not
Uh,
it will.
maths
so
and
we
not
s-
maths too.
so we so we only have single integral. So see, in single integral, that is out of the scope kind of. So just before the
Okay.
double integral, they treat us the. I mean, they actually teach us the gamma function.
Okay,
And the
okay,
first
okay.
gamma function encounter was the normal proof. I mean, normal mean is mu and sigma is
Ah,
sigma
okay.
square.
Got it,
So
got it.
only that there,
That's why,
only
that's why,
gamma comes
that's
up.
why. I think that's why you are facing difficulty. Okay. Okay, then let's not go then that. If you don't know what is that, so I mean, if you want, you can do the Google and all, or else after quiz two, we can discuss more on it, right? What is the gamma function and all.
Yes,
So
sir.
so far now, what you can keep in your mind. So PDF of your gamma distribution is nothing but beta raised power alpha, e raised power minus beta x, x raised power alpha minus one divided by gamma alpha. Okay. So these things and about what? Okay, about graph is clear. Graph. Okay, this is x raised power alpha minus 1 and this is something e raised power minus beta x, right? So this something your graph of your gamma distribution looks like. Okay, what you can do, x is greater than 0 also, and if you don't want this constant, so I can write down fx is proportional to x raised power alpha minus 1 into e raised power minus beta x. Okay, so you can just treat that. And one more information about your gamma distributions is you know about exponential distribution, right? Correct.
Yes, sir.
So
Yes, sir.
if I will add, suppose I'm saying x1 x2 xn are iid exponential lambda, right? Then sum of these xi will follow gamma n comma lambda. Okay, you can prove it also. You can see the what will be the this pdf lambda is for minus lambda x, right? For 1x, correct? So for summation of xi you can find out it will follow n comma lambda actually. And there is one more information. Expected value of gamma distribution is what? Alpha by beta, and variance of your gamma
Alpha by
distribution
beta square.
alpha by beta square. And you know what is the variance of expected value of exponential distribution? 1 by lambda, right?
Ha.
And
And
variance is
variance
1 by
1 by
lambda
lambda
square,
square.
right?
So you just scale that alpha times to get
Correct,
it.
correct. So accordingly it will change. Okay. So there is two more distributions. Let's just discuss about with the name and the PDF.
Sir,
Otherwise,
this exercise will just the exercise will follow gamma n comma lambda.
yes, n comma lambda.
Okay.
So
And then E of gamma will be
no, no,
alpha beta.
it's in general. It's in general. Don't you
Okay, in
think?
general.
In
Okay,
general,
okay.
if I'm saying x is following gamma, alpha, comma beta, then it's true.
Okay, fine.
Okay.
Okay.
So for in this case, it will be n by lambda and n by lambda square. Okay. So there is one more distribution, Cauchy distribution. Okay. So in the Cauchy distribution, actually, okay, how I can get the Cauchy distribution? Standard Cauchy.
So it's division of two standard actually. X by Y, something like that.
Yeah, it's I mean, if I have x following, let's say, normal 0 comma sigma square, y is following normal 0 comma sigma square, so x divided by y will follow the cos 0 comma. Okay, one second, just give me 3 to 4 minutes, I will come back. Okay, I was some emergency contact. Okay, just give me 3 to 4 minutes. Okay, sorry for
Okay.
that. Yeah. Yeah. Hello. Hello. Am I audible?
Yes, sir.
So
Yeah,
you're
yeah,
audible.
yeah, yeah. Sorry, sorry. Actually, there was some emergency. So, okay. So now, so let's do that. Just intro of those distribution. Okay, that chi-square and everything. Not chi-square. That Cauchy distribution. And all. So just let's see what is the some just intro about those distribution. I think. Okay. So another kind of continuous distribution is Cauchy distribution. It's called Cauchy distribution. So so suppose I'm saying x is following, noted as Cauchy distribution with there are two parameters. Let's say theta and alpha square. Okay. So PDF of this Cauchy distribution is given as 1 by pi that's by 3.14 value, and alpha divided by alpha square plus x minus theta square. So this is something PDF of we can define the PDF of your Cauchy distribution, and here theta called the actually name as something location parameter, and this is called the scale parameter alpha square. uh, but one important thing which is say in case of Cauchy distribution, mean, variance, and MGF all are undefined for this Cauchy distribution. We do not have mean, variance, and MGF of this Cauchy distribution. This is one important point of about our Cauchy distribution. Okay, and there is one property is of my about its Cauchy distribution. Suppose x and y are IID normal. I mean these two are IID normal with 0 comma sigma square, then x divided by y will be, it will follow Cauchy distribution 0 comma 1. I mean it's called standard Cauchy distribution. I mean here theta is the 0 and alpha square is the 1 actually. So x y are IID normal 0 comma sigma square, then ratio of these two will be standard Cauchy distribution. Okay, so this is just one information about your one of the Cauchy distribution. Another distribution, if I'm not wrong, it was beta distribution, right?
Yes, sir. Beta.
Yes, sir.
Okay. So okay. So I think for beta distribution there are two kind of beta distribution. I think we are yesterday going to study only one kind of. So beta, I mean it calls sometimes beta first kind of distribution. So we are study in stage 2. We are going to study this first kind of beta distribution. So suppose I'm saying it has also two parameter distribution family. So suppose X is following beta distribution with parameter alpha and beta. I mean these two are parameters of this distribution, and PDF, and it's of course alpha should be greater than 0 and beta should be greater than 0. So PDF of this beta distribution is nothing but it's proportional to x raised power alpha minus 1 into 1 minus x raised power beta minus 1, and your one important thing, x should be between 0 and 1. Okay, so basically this beta distribution is very useful when we are going to decide about prior distributions at all. I mean which will I mean when we will study about Bayesian estimation in the week 10 para, not I think, yeah, week 10 is there about Bayesian distribution. So beta distribution is very useful at that point to decide that, because beta distribution it help us to find out the likelihood. Okay, for example, beta distribution is useful like you know to rate the new movie, because suppose some new movie is going to be released, so ratings are there, right? Yes or no?
Yes, sir.
I mean,
Yes, yes, sir.
so ratings
Yes,
Yes,
are
sir.
there, right?
Reviews and ratings.
Yeah, so beta distribution is useful in that case, like we have to find out the likelihood of the audience rating that new released movie. So likelihood, what is the likelihood, we'll see in the week 10 actually. Likelihood nothing but defined as the product of PDFs actually. Product of each PDF. Like suppose x1, x2, xn are IID something distribution x. So it will be product of fx, xi, I is equal to 1 to n. So this is something known as likelihood. So this is in case of, you can say in this particular case, I can say likelihood of the audience, whatever our audience is there, rating the new released movie. Also, as I told you, this beta distribution is very useful in Bayesian analysis, right? To define our prior knowledge, correct? So, I mean, when you will study Bayesian distribution, there will be prior distribution, posterior distribution, and likelihood. So these all things are useful. So basically, this is the some information about my beta distribution. So suppose I'm saying x is following beta alpha comma beta. These two are parameters. and then PDF will be proportional to x raised power alpha minus 1 into 1 minus x raised power beta minus 1. Okay, that's the information about our this beta distribution, and the mean of that distribution is nothing but uh, it's alpha divided by alpha plus beta, and variance is something alpha beta divided by something is there. I'm not able to recall it, that one. Is there anyone who is able to recall?
So alpha plus beta whole square
Okay.
into alpha plus beta plus 1.
Okay. Okay, and don't worry about these formulas and all. Will be provided to you. Don't worry. But okay, so this some sort of idea is clear about beta distribution.
Yes, sir.
Okay. So, and one property about this beta distribution is also, suppose I'm saying X is following gamma distribution with parameter alpha and let's say one another parameter 1 by theta, and Y is also following gamma distribution beta comma 1 by theta, and these two are independent, then distribution of X divided by X plus Y will be beta distribution alpha comma beta. So this is one kind of property about your beta distribution. So I can assume you guys are getting this kind of boring kind of thing, right? Does
Actually,
it?
it's a bit more technical as compared to the other weeks we have.
Yeah, yeah, this is some technical. I mean, you must know some about function. Like for gamma distribution, you have to aware about gamma function and all. If you want to relate it more closely, but for this week especially, we have to just intro about this kind of distribution. What is your, suppose as we know, if X is following normal, then what is the PDF, what is the mean, what is the variance? Similarly, if X is following gamma, what is the mean, what is the variance, what kind of PDF PMF looks, and not PMF PDF looks like. Similarly about Cauchy distribution, and same about your this beta distribution. Okay, I mean, meanwhile, by a quick I mean, are you getting the quick I mean, some basic idea or not? I mean, suppose this is this and like that. I mean, are you able to relate it or not?
Yes, sir, like somewhat.
Somewhat, huh?
Huh.
Okay, okay, that's it, no problem. I think about next topic is about distributions of your sample mean and all, right?
Yes, sir.
Those are, I think, yeah,
That is fine.
fine for everyone, or do you want
Okay.
to go through it once? Yes, no?
If that doesn't require too much of time, it will be better if I can shed some light on that.
Okay, sure, sure, no problem. So that's, I think, why I was saying like that, because those kind of things we have done earlier a lot of time. So distribution of sample mean and all. I mean, suppose I have x1, x2, xn. Let's say these all are IID normal mu comma sigma square, right? So what will be the distribution of sample mean? So what is the sample mean? So sample mean is defined as summation of xi divided by n, right? This is something I can define the sample mean, correct? So sample mean, you have to find out the what is the distribution of sample mean. So what is the, what will the mean and the variance of this for this x bar? Okay, so we have to find out that one. And one more thing before going to that, so x this x bar is nothing but x1 x2 plus xn divided by n, right? So this is the linear combination of IID normal random variables, correct?
Yes, sir.
And we know some of the IID normal variables is random, normal random variable is again normal, right?
Normal. Yeah, yeah.
So for this x bar, what is the expected value of x bar? It will be
Uh,
mu plus so on,
huh.
mu
N
divided by
into
n,
me.
and mu
Yeah.
divided by n, again mu, right?
Huh.
Correct. And what is the variance of x bar? So
Sigma
it will
square.
be variance of 1 upon n summation of x size,
Ha ha
right?
ha. Yeah, yeah, yeah.
So it will be 1 by n square variance, sum of variance of xi, since all are
Ha,
IID,
ha.
correct? So it will be n
Sigma
times
square
sigma
by.
square divided by n square. So it will be n will get cancelled. I will get sigma square by n. So that's all about distribution of your sample mean in this for this normal random variable. Okay. I mean, this can be true. This is true for any kind of distribution. It's not about only normal. Suppose it's x IID x, and for this random variable x, mean is mu and variance sigma square. So it's true in general also. Okay. Okay. So this is okay so far.
Yes, sir.
So there are some again some technical kind of things, something which you just idea about those things. So what is the chi-square? How I can get the chi-square?
Oh, that n of those gamma, like the squared normals.
Yeah, so basically chi-square is nothing but sum of squares of normal samples. Okay, sum of squares of normal samples is the chi-square distribution actually. So chi-square distribution. Now you are people like what is the chi-square distribution, right? So should we go that point?
Yes, sir. Everything is happening. You can just summarize that as well.
Okay. So okay. So let's do with the help of, I mean, that standard normal. Okay. I can do the same thing with the help of normal 0 comma sigma square, but let's go with the standard normal. So suppose I have x1 x2 xn standard normal variables. Okay, 0 comma 1. Then if I will then uh, okay, initially I took the as a standard normal. Then if I will take the square of these normal random variables, right? Let's say x1 square, x2 square. So sum of these standard normal variables will form the one of the distribution which is called the chi-square distribution basically. Okay. So let me write down the things. So for the chi-square actually. So okay, suppose I have x is the, let's say I'm saying it's a normal mu comma sigma square. How I can get the standard normal variable? X
X minus
minus
mu
mu
by
by
X minus
sigma.
mu by sigma.
So this is standard normal variable, right? So now, as I told you, square, right? So if I will say the square of z square, so it is follow chi-square distribution with one degree freedom. So this is called something degree freedom of that for that this chi-square distribution. So before, okay, so suppose instead, so here I had one random variable, right? Suppose I have n independent random variables x1, x2, so on, xn. These all are normal, independent, normal. So in general, suppose I'm saying xi is independent, normal. Let's say mu I comma sigma square. Okay. Then how I will convert into the standard normal variate? So zi will be what? Xi minus mu I divided by sigma I, right? It will be normal 0 comma 1. Yes or no?
Yes, sir.
So chi-square distribution is defined as nothing but sum of square of this standard normal variate is called the chi-square distribution with n degree of freedom. Okay, so this is something called n degree of freedom. How many? It depends on how many random variables are there. So it's called the something n degree of freedom actually. Okay,
Yes,
yes
sir.
or no? So I think
Yes, sir.
sir has taken about instead of normal 0 comma 1, sir has taken the normal 0 comma sigma square variables, right?
Yes, sir.
Okay.
Yes,
So
sir.
that will not affect that much. It's same thing. Okay. So now, so one more property is there. So since this chi-square means since summation of zi square I is equal to 1 to n, so it will be I is equal to 1 to n. That means xi minus mu I, that is sigma I square. That is something we are doing, right? So this is the same as gamma distribution with parameters half and n by 2. Not getting a.
So now I'm getting confused. There was n by 2
Same
comma
thing.
1 by 2 sigma square. Now this is getting confused for me.
Okay. Okay. No, no. That okay. Okay. That was for when x is normal 0 comma sigma square, right?
Huh.
Ha 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 ha.
I have taken standard normal variable.
Okay.
Not getting. See, it's not n by 2. It's a gamma n by 2 comma 1 by 2 actually. So I
Huh.
think you had n by 2 comma 1 by 2 sigma square you are talking about, right?
Yes, sir. And the
So
sigma square will
Ha ha.
become 1.
okay, okay, that's the same because I have taken this as a standard normal, right? Sir has taken for the normal 0 comma sigma square, right?
Yes, sir.
See, if I'm not taking sigma square, that means it's a 0 comma 1, right?
Yes,
Ha, then
sir.
it's 1 by
Then
2.
it's
Ha ha ha.
Huh.
n
Yeah.
by 2, 1 by 2. Yeah, yeah.
Okay, I was about to say this one actually.
Ah, okay.
Okay. Okay, so are you getting this idea? So something about chi-square and all.
Yes, sir.
Okay.
Yes, sir.
So this is something just an intro about chi-square distribution. So basically, chi-square distribution is much useful, like in case of to know the independence kind of things. Independence means what? I mean, independence of that that contingency table which we have done in stats one.
Yes, sir.
Are you? I mean, can you recall that one?
Ha ha
Conti-
ha.
Contingency table of. I mean, we are making that contingency table to know the association between two categorical variables and all, right?
Yes, sir.
Yes, yes, sir. Yeah,
Okay.
yeah.
So something like that. So basically, in chi-square, we are doing like that because chi-square is much useful to know the independence of attributes. Okay, attributes means suppose there are two kind of population. One is suppose one proportion of population, one kind of attribute. So it's just one kind of attribute. Suppose one kind of proportion is following, they are like rice. I mean, they are like to eat rice. I mean, rice lover kind of things you can say. Another people is have some kind of another attribute, they are wheat lover kind of things. Okay, so whether they are independence or not, independent between those two attributes is there or not kind of things. I mean, that is something different thing. And it's also useful chi-square when we have to know the goodness of fit test and all. Okay, anyone of you done? No, I think you guys have not done that BA course. In BA, chi-square distribution is much useful actually.
Sir, this n by two and half thing, like where you are relating this is from?
Okay, so this is the one of the property you can get. I mean, if you find out the distribution of this n by 2 1 by 2, right? So this will be same. Okay, what is the gamma distribution I here? It's initially I had beta raised power alpha. Okay, let's do the proportional sign. So x raised power alpha minus 1 e raised power minus beta x, right?
Yes,
So
yes.
at the place of alpha I here n by 2 minus 1, right? And in the place of beta I minus x by 2, correct? And I'm saying if you see the PDF of chi distribution, I think chi-square distribution PDF is not, sir has not done, right?
No, sir.
Yes,
He
sir.
just said that like the parameters are n by 2, 1 by 2 of gamma.
Gamma,
Yeah.
okay. So let me just write down the PDF. So PDF of chi-square distribution, just give me a minute. So PDF of chi-square distribution is nothing but it's I'm not writing the constant, I'm writing just uh, variable value. So e raised power minus chi-square by 2. It's not x, so let's say, let me denote, I'm saying x, suppose x is following chi-square, okay? So fx x is this is proportional to e raised power minus x by 2 and x raised power n by 2 minus 1 dx. Okay, and range of this is 0 to infinity. So this is something PDF of chi-square distribution. So this is the same as this one, right? Or not? Are you getting? So this
Yes,
PDF
sir.
part is same as this PDF, right? So that's the same thing is saying here chi-square. Okay, so suppose I have gamma n by 2 comma 1 by 2. So this is same as the chi-square distribution. That's the point they want to say. Okay, actually PDF of your chi-square distribution, it's nothing but let me write down that constant value. It's a 1 upon 2 raised to power n by 2 gamma of n by 2 e raised to power minus chi square divided by 2 and chi square raised to power n by 2 minus 1. So this is something chi square distribution, and these things you can get when you will add the NIID, an independent standard normal variable. Okay, these all things are actually related, actually connected. So chi-square we are getting by adding an independent standard normal variable, and if chi-square is there, then that chi-square is the same as gamma n by 2 comma n by 2. Actually this things is same as this one. Okay, are you getting the idea? Basically, okay, this is the PDF of chi-square. Okay, this is okay.
Yes, sir.
Yes, sir.
So this, I mean, these all are interconnected, right? We are getting the chi-square with the help of gamma. No, sorry, with the help of normal, and gamma with also with the gamma function, like that. So we should be aware about some basic kind of thing, actually. So this thing, okay. So as I have told you, the gamma distribution, it was beta raised for alpha, right? And x raised for alpha minus 1 e raised for minus beta x and divided by alpha raised for beta. This was there, right? So what I'm saying, this chi-square is same as gamma n by 2 comma 1 by 2, correct? So what is, it's a 1 by 2 raised for n by 2, right? And x power alpha means n by 2 minus 1, and e raised for minus beta, so minus x by 2, and alpha raised for beta, so alpha is n by 2 raised power half. Okay, so this is something you can get the same value. Okay, something like that. So if you are not going to consider that proportional sign, sorry, equal to sign, so if you treat this proportional sign, so you will get the same value, actually. Is this okay? Somewhat you are getting the idea?
Yes, sir.
Yes.
Okay.
So,
We'll have
so
to
how far?
rewatch the video.
Yeah, yeah.
We'll have to rewatch the video.
Yeah. So actually, in week 8, basically, only two concepts are very important. That was MGF and central limit theorem. Okay, that's are very useful as your exam point of view also. These all about distribution which you are discussing about, these all distribution. So these were just a general idea about your distribution. I mean, I think you people are facing difficulty because we have not seen this distribution before, right? Just like we are much familiar with the binomial, Poisson and all, but these are just an intro about that distribution, because we will use this distribution in further. Okay, so these are just an intro. I mean, some, what is the property, like, see, we are getting the binomial to Bernoulli, right? If I will add some NIID Bernoulli random, I will get binomial, right? So similarly,
Yes, sir.
how I can get the chi-square? If I will add the square of NIID an independent standard normal way, I will get chi-square. This chi-square is same as the gamma n by 2 comma 1 by 2. Like that. I mean, these all things are some interconnected. Like this, I can get the Poisson distribution to binomial. How? Anybody?
So it's a limiting case of binomial.
Limiting. I mean, your p should be,
Should be
small,
very
n should be
small,
large, then
be
so
tending
that
to
product of
infinity.
np should be some constant,
That is
so
lambda.
then it will be Poisson distribution. So there are all the, I mean, there are some property and the distributions are interconnected. So that's the things we are discussing here. I mean, you are getting difficulty because of this distribution you are studying first time. So in this week, just a idea. I mean, suppose x is following this distribution, what is the PMF? How PMF, not PMF, PDF looks like, what is the expected value, what is the variance and all, everything, like, right? So these are just an intro about, don't worry about that, like how we are how we'll solve the question and all. We'll do that one, we'll do the, those things also. Okay, but these all are just an intro about some. Okay.
So will you be releasing the solve with us slides for week 8 before the
Uh,
session?
okay. So, okay, I will come to that. Okay, so far it is okay. I think we have covered all the concepts, right?
Yes, sir. We've
Yes.
covered all the.
Is there something else?
No, sir. I think that was all the concepts that
Okay.
were in the lectures.
Yeah. So basically, what was the to discuss about this? I think this last some topics. I think you got some. Uh, maybe you got bored, right? But don't think like that. It's these all things just about just intro about some distributions. Okay. So for the okay, let's. Is there any question related to activity practice and all or something? So we can stop the streaming if there is not something like that. Then we can discuss
Sir,
what
the last activity question, like of lecture 4, after
8.4.
8.4, the third one, I was a little confused.
Okay. X1, X2, X1, X2, X3, X4 are normal zero. What is the variance of yeah? So what is the problem?
So 1 second.
It's
See,
gamma, right?
it's a gamma because x1 square plus x2 square plus xn square is the gamma n by 2 comma 1 by 2 sigma square, right?
Right.
So it will
Okay.
be n is 4, 4 by 2 comma 1 by 2 into 4.
Okay.
Okay, and
Yeah.
you know what is the variance of gamma? Just find out the parameters and alpha by beta square is the gamma
Okay.
variance of the gamma distribution. Okay.
Okay.
So don't worry about these kind of things during the quizzes. Okay, all the formulas will be provided, but CLT and MGF are more important kind of thing. Okay, if there is not any something technical, we can stop the streaming and we'll discuss the some general one. Okay, so for okay that to solve with the slides. So what guys you want? I mean, should we release before or we can if you want solving during the session?
I mean, I found it very useful to have the slides beforehand because then I could work it out on my own before the session. So
Uh,
those were quite good the last time it was released early.
okay. Last time, yeah, because we had less time, so that's why we had released. Sorry.
So I feel if we can solve it during the session, that's really good. But if we don't have time, or like if the sums are very tedious, then getting it before is useful.
So there are two slides. I mean, for week 7 as well as week 8. Okay. So we have planned no, to do that solve the session tomorrow and day after tomorrow. Okay. So there are two options. Whether first one is we can do it during that session also, or else we can release it before, okay, as a PDF. And if you have any difficulty in those problems, we can discuss it during the session.
Yeah, I mean, I have no problems with week 7. It's
Uh,
just the week 8 because of
yeah,
I
in
think.
week 8, suppose CLT is there, CLT will be most probably, then CLT and MGF, okay. And you know key idea about CLT, just convert into the standard. Yeah, we'll release. So week 7 we'll do in the session, or else I will check what we can do. Otherwise, we'll release tomorrow morning, right? Tomorrow morning, both of them. Will that be okay?
Yes, sir. That'd be great.
Okay.
Thanks.
Yeah. Okay. So, is there anything else, or we can stop the streaming? Yes. No.
So nothing related to, I mean, I
Okay.
have something to ask you. I mean, related to PYQs.
Yeah.
So,
Actually, I had to look into that. Right. You asked me. Actually, I got stuck somewhere.
no, sir.
Okay.
No, sir.
Uh,
Apart from those, I have one more question actually.
okay. Then let me stop the streaming. We'll discuss some general things. Okay. Yeah.
Okay, sir.